Did you get notice?
Yes, ma'am.
Yes, madam.
Okay. So we were discussing some terminology of graph, right? So in last class, how many types of graphs discussed about how many types of graph? Can you please just remind me that which structures I discussed in the last class?
Graph.
Yeah, but there are some types of graph, isn't it?
Yes, ma'am. Connected. Five.
Connected.
Weighted graph. Directed.
Okay.
Directed and undirected graph. Then simple and complete graphs. Dense and sparse graph.
No, I didn't talk about dense or spare graph.
Okay.
In the last class, I mainly talked about simple graph, that what is actually graph or when we can call a structured graph, right? Or how we can identify when a structure is given, how we can identify that this is that type of graph, this is a complete graph or this is connected graph. So we discussed about simple graph or a general graph, then connected graph, complete graph, multi-graph, weighted graph, then tree graph, and the last one was directed graph. So there are 7 types of graph. So we can start with the first one. What is just a graph? A graph consists of 2 things. One is its vertices and another is the edges. So what is vertex or what is vertices? A graph can have some members, some nodes, right? Suppose A, B, C, D. These are some nodes of a graph. Right, so now how you can create the edge? Edge is the relationship. Edge is the connecting line or edge connection between any 2 nodes. So suppose A and B are connected by this edge, this E1. B and C are connected. Then A and C are also connected, and D is connected with C. So what is it? Is this a graph?
Yes, ma'am.
Yes, ma'am.
It's a graph. And what type of graph it is? It is just a simple graph. So in a graph, all the nodes are actually connected with some other nodes. Here A is connected with B, A is connected with C, and B is also connected C and D. They are also connected, right? Or when we are connecting this one, suppose now there are edges between any 2 nodes. So what kind of graph it is?
Connected graph.
Simple connected
graph. Why it is connected graph? Because now between any 2 nodes, that 2 nodes can be A or D, A or B, B or C, C or D, A or C. Between any 2 nodes there is an edge. That's why this graph is connected graph. Or when we can call it complete graph. In complete graph, one node is connected with all the other nodes of that graph. In this graph, the total number of vertices are 4, or total number of nodes are 4. That means one node can be connected with 3 nodes. A can be connected with B, C, and D, and B can be connected with A, C, also D, and C is connected with B, A, and D. So this is a complete graph. But these graphs are undirected. Why? Because we don't know the starting point or the end point of these edges. We can assume that D is the starting point and A is the end point, or we can take A as a source node and D is the destination node, because these graphs are not directed graph. Okay, so when you can call them weighted graph, if some values are assigned to each of these edges. If E1 equals to 2, this is E2 equals to 4. So when we are assigning some values to these edges, that means when each of these edge has some weights or values, we can call it weighted graph. Okay, so in these graphs, we can use some other terminologies, that is simple path or path sequence or closed path, loop or cycle, right? But before that, we need to know what is adjacency node. Each of this node has some neighboring nodes or adjacency node, right? So how you can create that adjacency list? If A is a node, now find out how many edges started from that node A, or how many edges contains that node A. So here, one, two, three nodes started from A. Okay, so here A is connected with B, it's connected with D, and it's also connected with C. That's why it's which nodes are its neighboring nodes, B, C, and E. And another term was degree. What is degree? To find out for how many edges
Number of
that node
vertices.
is the beginning. Degree is not actually number of vertices. Degree is, suppose you want to find out what is the degree of A. Now find out for how many edges A is the starting node. A is a source node. This is undirected graph. So just find out how many edges are connected with that node A. So there are
Three nodes.
three edges from A to B, A to C, A to D. These three edges. Okay, so we can so we can say that the degree of A is 3. Right? So now the path sequence. What is path sequence? In graph, if we want to find out the path sequence, then we need to take two nodes. One is our starting node or source node, and another is the end node or the destination node. So we want to find out what is the path length between D and B. What will be the answer? Path's length. That is, you have to find out the way or the path for traveling from this point, from the source node D to the destination node B. And in this graph, this undirected graph, so you can find several ways. The first one is D to A, then A to B. So here the path length is 2 because between these two nodes there are two edges, one from D to A, another from A to B. So here the path length is 2. But what is the path sequence? In path sequence, you have to take all the nodes, including the starting node and the end node. So here the path sequence is D, A, B. Okay, so can you find any other path length or any other path sequences length too?
DCB path sequence 2 line.
DCB. DCB is another way for traveling from node B to node D to node B. Okay, so these are what kind of paths there? They're simple path. Why? Because look at the path sequence. All these nodes are unique or distinct. D, A, B, all these nodes are taken only once. So we can call it simple paths. Okay, so now find out how many cycles are here. What is cycle? If we start from a node, suppose we have started from A, so now you have to find out all the possible locations, all the possible directions for traveling to that node again. How we can reach, after starting from this point, how we can reach to that point again. So now look at this sequence. One is A, C, D, A. This is a cycle. What is cycle? If the starting node and the end node is same, but between that two nodes there can be some other nodes. This is called cycle. So here A, C, D, A. This is a cycle with length 3 because there are 3 edges. Okay, another cycle is for A, B, C, A. This is another cycle with length 3. Okay, another one is A, B, C, D, A. This is another cycles of length 4. So in cycle, the starting nodes and the end node is same, but between them we can have some different nodes. That is cycle. And is there any closed path here, or is there any loop here? No. What is a closed path or loop? If the starting node, suppose starting node is U and the end node is V. When U equals to V, that means if A is a source node, then after starting from this node, if we can directly reach to that node again, that is called a closed path, just like this one. But we didn't take any closed path or any loop. So this this graph doesn't have any loop. So these are some terminologies, and then there are some other types of graph, that is multi-graph. So what is multi-graph? Here in simple graph, we don't have multiple edges between any two nodes, isn't it?
Yes, ma'am.
This is a graph A, this is a graph with four nodes A, B, C, D, and there are five edges. So here the edges are E1, E2, E3, and this is a connected graph, right? E4, E5. So did it take two edges between any two nodes? Did it take more than one edge between any two nodes? No. So we can't call it multi-graph. So what is multi-graph? In a multi-graph, we can add several edges from the same starting point and to the same end point. Suppose here this HE1 and E6 both have started from the point A and their destination node is B. So this is multi-graph. And in multi-graph, if we want, we can assign some loop also. This is multi-graph. Okay. And what is tree graph? The main characteristic of tree graph, you know, that in a tree graph, if number of node is n, then the number of edges will be n minus 1. Why? Because in tree graph, all the simple paths are unique paths. That means for traveling from one point to another point, we can't find more than one way. That's why all the paths are unique simple paths. That is tree graph. Okay. So now what is directed graph? In directed graph, the direction will be given, so we can easily find out which one is the starting node for that edge and which one is the end node. Suppose this one. So A, B, C, D, and there is an edge. And in a directed graph, if we want, we can take multiple edges. These edges are called parallel edge. What is parallel edge? Look at this. For these two edges, the starting node are B and the end node is A. So when two edges have the same source node and the same destination node, those edges are called parallel edge. Okay. Then this directed graph can have some loop also. So here the directions will be given. Suppose the first edge E1. So for E1, which one is the starting node? D, because this edge have started from here, from D2, and now it reaches to the point A. So for E1, the source node is D and the destination node is A. Then from C to D, from B to D, from C to D. So what kind of graph it is? It's a directed graph, or you can take a loop here. And that loop also will be a directed loop. So in this graph, how many edges are here? 1, 2, 3, 4, 5, 6, 7. So E1, E2, this is E3, E4, E5, E6, and E7. So now from this graph, can we find out what is the in degree or out degree of a node? From this graph, we can easily create the adjacency list, isn't it? For A, how many adjacent nodes are here? For A, for this node, the adjacent node is 0. The node A doesn't have any adjacent node, isn't it? Look at this, look at the graph. Is there any edge which is started from A?
No, ma'am.
So that means for A, there are no adjacent node. What about D?
1, ma'am.
One adjacent.
Only one. Only A is adjacent node of D. What about C?
2.
C is the beginning of how many edges? 2 edges. So for C, the neighboring nodes are D and B. What about B? A, D. These are the neighboring node of B. Okay, so now can you find out the in degree and out degree of all these nodes A, B, C, D? For A, the incoming node is 3.
3, ma'am.
because there are three edges which ends at the point A. So for A, the in degree is 3. But what about out degree?
Ma'am, 0, ma'am.
0. Why the out degree is 0? Because from A, there are no, A is not the starting point of any of the edges. That's why it's out degree is 0. Okay, so when a node has positive in degree but 0 out degree, that node is called sync node. What is sync node? If the in degree of that node is a positive value but the out degree is 0, that node is called sync node. Okay, and there is another kind of node, that is source node. What is source node? If the number of, or if suppose that node has some positive out degree but the in degree is 0, is there any node which is source node? The out degree is positive value but the in degree is 0.
CBD.
CBD.
All three are, you can consider.
All three are source node.
Ma'am,
What are
C,
the
ma'am.
in degree? What is the in degree of C?
In degree is none.
0.
Very good. In degree is 0. For C, the in degree is 0. So this is a source node. Very good. This is a source node. Is it clear what is sync node and what is source node?
Yes,
If the node has some positive out degree but the in degree is 0, that node is source node. If a node has some positive in degree but the out degree is 0, that is sync node. And what is parallel edge? If two edges begins from the same node and ends at the same node, that is called parallel edge. Okay, so these are some terminology of graphs. So I hope you can easily identify that the given structure is what kind of graph. You can easily identify it. So now the next topic is graph traversal. What is traversal? Traversal means accessing or visiting the nodes, all the nodes of a structure. And in tree traversal, how we traverse all the nodes of a tree by using some mechanisms, by using some methods, that is in order, pre-order, post-order, right? So how we can traverse all the nodes of a graph? The next topic is graph traversal. And traversal means you have to process all the nodes exactly once. You cannot visit a node twice. So there are two ways for traversing the graph. One is BFS, or it's called breadth first search. And number 2 is DFS, or depth first search. Okay, so there are two ways. First, we'll discuss about BFS, breadth first search. Okay. Suppose a graph is given. So the first node is 0, and this is an undirected graph. 1, and from 1 to 2, 2 to 3. 1 and 3 are also connected, and 0 and 3 are connected. And then 4, 3 and 4 connected, 2 and 4 are also connected. Then another node is here, that is 5. We can place 5 here. 1 to 5. And you can take one more node, that is 6. 4 and 6 are connected, as well as 1 and 6. Okay, 2 and 6 are also connected. So what kind of graph it is?
Connected.
Yes, it's a connected graph. Okay, so now in this graph, the total number of vertices are 7. 0, 1, 2, 3, 4, 5, 6. There are total How many vertices are here? Total 7 vertices. And if we want to apply this traversal method, that means we have to traverse each of these nodes exactly once. That means if it is our output or it is the result array, here we have to take all the nodes exactly once. And how we traverse the array? In array, we traverse the nodes from sequential memory location. At first, we'll traverse the nodes from memory location 0, then from 1, 2, 3. But graph is nonlinear data structure. So here we can start from anywhere of this graph. We can start with any nodes of the graph. If we want, we can take 3 as a source node, or 2 as a source node, or 5 as a source node. It depends on us. Okay. So suppose we want to start from 0. So now we cannot store those nodes in the result directly. In BFS, we usually use a queue. So what is queue? It's a linear data structure. And what type of data structure it is? It is called first in, first out data structure, or FIFO data structure. Right. So in queue, how we insert or delete the element? Both ends are open. Suppose this is the queue, array representation of the queue. So the front end and the rear end are open. Both ends are open, and you can use the rear end for inserting the nodes, and the front end can be used for deleting the nodes. And which element will be deleted first? The element which came first, which inserted first, that is queue, first in, first out data structure. So in BFS or breadth first search method, we'll use a queue. Okay, so here there are 7 nodes, and we know what is the concept of adjacency list. We know how to find out the adjacent nodes, right? So if we start from this node, that means 0 is the source node. So at first, the first item on the first node will be inserted in the queue. This is the first memory location, so we can insert 0 here. You can take any other nodes. You can take 1, 2, 3. You can start with any nodes of the graph. Okay, suppose this is our starting point. 0 is the source node. And now, after inserting a node in this queue, if we want to traverse it, suppose now we want to delete that node from the queue. After traversing that node, now we want to delete it from the queue. So at that time, at first, you have to insert all the adjacent node of 0 in that queue. Then you can print that queue in this result. If we want to delete 0 from this queue, what is the way? At first, we have to store all the adjacent nodes of 0. So here we can create the adjacency list. So for 0, which nodes are the adjacent node? 2 nodes, 1 and 3. For 0, the adjacent nodes are 1 and 3. So now in this queue, you can insert 1 first and then 3. Or if you want, you can insert 3 first and then 1. So we can insert 1 first and then 3. So after deleting that node, or at the time of deletion, you have to insert all the adjacent node of that node 0. And then you can print the node in the result. Okay, so what is the next step? Again, we are going to traverse all the nodes. How? At first, we have to traverse all the adjacent node of that node 0. So there are 2 adjacent nodes. Now, if we want to traverse the next node 1, this is queue, first in, first out. So 1 was inserted before 3. That's why now we will traverse that node 1. So at the time of traversal, or when we'll delete that node from the queue, now you can insert all the adjacent node of 1 in that queue. So which nodes are the adjacent node of 1, 0, 3, and 2 and 6, also 5. But one thing is, you cannot insert the visited node in the queue, or you cannot insert the node in the queue which is already inserted. So for 1, these are the adjacent nodes 0, 3, 2, 6, 5. But look at the queue, or look at the result. 0 is already visited, so we can't visit it again. Then 3 is already inserted in the queue. So we'll only insert the nodes 2, 6, 5, and you can insert them in any order. Suppose you are following this order 2, 5, 6. If you want, you can insert 6 first and then 5, 2, or 5, 6, 2. Okay, so this is our queue. And here we can print 1. That means we already visited the node 0 and we already traversed the node 1. Now look at the queue. The first node in the queue is 3. That means now we have to traverse that node 3. And now the same thing, if we want to delete that node, then insert all the adjacent nodes of 3 in that queue. So what are the adjacent node of 3? 0, 1, and 2. But you can only insert the unvisited node. So among those three nodes, 0 is already visited and 1 is already visited and 2 is already inserted in the queue. So now we don't need to insert any new node in the queue. We can simply print that data or node. Now again, in this queue, 2 is the first data, so it will be removed first. Now we can remove that data from the queue, but before deleting that data, you have to insert all its adjacent nodes. So for 2, the adjacent nodes are 1, 3, 4, and 5. 1, 3, 4, 5. Now find out which nodes are already visited. 1 and 3 and 5 is already taken in the queue, so we can insert 4. Okay, so after that you can print 2 in the result. Now again look at the queue. 5 is the first element, so now you can traverse that node. So now at the time of traversal, at first insert its neighboring node. For 5, the neighboring nodes are 1, 2, only these 2 nodes, right? And 1 and 2 are already visited. So we don't need to insert any new node, we can simply add that node in the result. This is our visited node. Now the next one is 6. So if we want to delete that node, at first insert all its neighboring nodes. For 6, the adjacent nodes are 1, 4, only these 2 nodes, 1 and 4. Okay, so now this 1 is already visited and 4 is already taken in the queue. So we can simply print that node 6. Now in this queue, there is only one element left, and that is the first element of the queue, that is 4. So you can simply or find out the adjacent node of that node 4. For 4, the adjacent nodes are 3 to 6,
1,
which are
2, 3,
y 1.
5, 6.
For 4, the adjacent nodes are 3, 2, and 6. And all these nodes are visited. So we can simply add that node in the result. So now this node is already visited. So in this way, look at the result. We visited, we traversed all the nodes of this graph. And this is BFS or Breadth First Search Traversal method. So how we traverse all the nodes here, we just have to start from one node, and that node is our source node. Now we can at first we can traverse that node, and all the adjacent node of that node should be traversed first. That means whenever you're deleting some node from the queue, and all the adjacent node of that item, that node, in this way, this queue, so sequentially we have to remove the nodes from the queue. Is it clear what is BFS? Hello, is it clear what is BFS?
Yes, ma'am.
So we can try another one. Okay, so I'm giving you another graph. A, C, D, so now in this graph, there are only 5 nodes. Traverse this graph using BFS method. How many nodes are here? Only 5 nodes. So use BFS for traversing all the nodes. And you can start with any node. And another thing, the sequence of the result can be different. By using this traversal method, we can create different sequence. Why? Because Hello? Hello?
Yes, ma'am.
Yeah, so what is the output? Do you need more time? Hello? If we start from this node D, okay, suppose our source node is D. So if we traverse this node first, so which node will be inserted in the queue? The first node is D, and suppose this is our queue. So at first, D is inserted in the queue. Okay. So after that, when you want to delete that node from the queue, which nodes will be inserted? Obviously, it's neighboring node that is E, C, and B. So this is our output. At first D will be traversed, and then now which element will be taken? Which node will be traversed next? Obviously E, because it's Q. So when we delete E from that queue, or before deleting it, we have to insert all the adjacent node of E. And how many adjacent nodes that node AE has? How many adjacent nodes of E? One is C, now there is A and D. The adjacent node of E is A, C, and D. And we just inserted one element C, so here we can take A and D is already taken, so only A. So after that, E can be listed here in this array. So now the next node will be C. So if we want to delete C from the array, then which node will be inserted here? All the adjacent node of C. And C has how many adjacent nodes? 4. That is A, E, B, and D. So D is already visited, and then A is already inserted here, and then E is already visited, B is already taken here. So now we can simply add C. Which node will be traversed? Then it's obviously B, isn't it? Can you all hear me? Hello?
Yes, ma'am, I can hear.
Okay, so if we want to delete that node from the queue, so which node will be inserted in the queue now? The adjacent node of B, right? So the adjacent nodes are A, C, and D. D and C are already visited, and A is already in the queue, right? So we can simply traverse that node B. Now the next one is A. So A has how many adjacent node? Only 2, C and B, and they're already traversed, so you can take A. Okay, so the output can be different. Suppose you got the sequence A, B, D, C, E. So it's also correct. Is it clear what is BFS or breadth first search?
Yes, ma'am.
Okay. So now the next one is DFS or depth first search. So what is the difference between BFS and DFS? In BFS, we have to use a queue. Okay, but in DFS, we usually use a stack. That is the main difference. So we'll use the previous graph, this one. Now we will take a queue, sorry, stack. So what is stack? This is also a linear data structure, but what is the property of stack? This is called last in first out data structure, right? So this is a structure where one end is always open. That is the top end of this array, right? So in this top end, we can insert or delete any element, right? And the last element will be removed first, that is stack. So how many nodes in this graph we have added? There are 4 nodes, 7 nodes. 0, and then 1, 5, This is 6. And this one is 2. This is 3. The last one is 4. Okay. So now, if we are using a stack, then how we can insert the data in the stack? In stack, always the topmost element will be removed first, or we can use the operation push or pop. Right. In BFS, we just started with one node. That was our source node, and when we want to delete that node, we have to insert all the adjacent node of that node. But in stack, we will not store more than one node at a time. Suppose 0 is the source node. This is our result or output. And in this stack, we'll insert only one node, that is 0. Okay, so initially the stack was empty and the value of top was 0. But now suppose here the location is 1. Okay, so after that, now which node will be inserted in the stack? Or if we want to traverse that node 0, we can add that node in the stack as well as we can add it in the result. Okay, so now 0 has how many adjacent nodes? 2 adjacent nodes, 1 and 3. So which one we should take now? Like BFS, in BFS we can insert all the adjacent node of a node. In DFS we can take only one adjacent node. And that node can be 3 or 1. So suppose we want to take 1. So after that, that node 1 will be traversed. And now 1 has 4 adjacent nodes. 0 is already visited, 3, 2, and 5. 1 has how many adjacent element? 4. 0, 3, 2, and 5. So 0 is already visited. We can take any one from these 3 options, 3 to 5. Suppose we want to take 3. So now 3 will be traversed or visited. After that, find out which nodes are the adjacent node of 3. There are 4 nodes, 0, 1, 2, and 4.
Ma'am,
0 and 1, sorry?
1 has 5 adjacent nodes.
Which one? 1. Yes, 1
0,
has.
0, 3, 5, 6.
Yeah, very good. But in stack, we'll only take one adjacent node. Okay, that node can be any one. You can take 2, 3, 5, 6, or 0 is already visited, so you cannot take 0. Okay, so now our current node is 3. So after that, you have to find out which nodes are the adjacent node of 3. There are how many nodes? 3 nodes. Sorry, 4. 0, 1, 2, and 4. 0 and 1 are already visited, so we can take 2 or 4. Okay, so we can take 2. So now this is the top of the stack. So now we can traverse 2. So if we want to traverse 2, then we have to find out the adjacent node of 2, and then we can add one adjacent node in the top of the stack. So 2 has how many adjacent nodes? 4. That is 1, 3, 4, and 5. 1 and 3 are already traversed, so 4 and 5 can be taken. So we can take 4. Okay, so now this is the top of the stack, so we can traverse that node. Here in DFS, we will always traverse the topmost node. So when we are traversing that node 4, now insert some nodes, some adjacent node of 4 in stack. So 4 has 3 adjacent nodes, 3, 2, 6. 3 and 2 are already visited, so we can take 6. Okay, so now this one is the top of the stack. So we can traverse that node. After that, we have to insert an adjacent node of 6. So this node 6 has how many adjacent nodes? Only 2, 1 and 4. But 1 and 4 are already visited. So how we can move forward? Because in BFS, how we traverse the node? We traverse all the adjacent node of a node. But in DFS, how we are moving forward? We are just taking one node and then we are taking one adjacent node of that node. In this way, we can move forward. But here in this point, now 6 has 2 adjacent nodes and both are visited. So how we can move forward? 5 is unvisited node. We didn't traverse that node yet, but there is no connection between 6 and 5. There is no edges, so we can't take 5. So what is the now? What is the way? In this point, this is a dead end because we cannot move forward. All the connected nodes of 6 are already visited, so how we can now move forward? It's not possible. So the only option is backtracking. That means we have to now go to the backwards. So how we can go backward? It also depends on this stack. So now the current node is 6 and 6 is connected with two nodes 1 and 4. So if we want, we can go backward in this way, 6 to 1 or 6 to 4, but we can't make the choice. It depends on the stack. So look at this. If 6 is the topmost element, after popping up that element, after deleting that element, now 4 is the topmost element. So how we can backtrack, how we can go backward in this direction, 6 to 4. This is backtracking. Now we're going to the reverse order, going to the previous nodes, but we are not adding any node in the result because 4 is a visited node. Okay, so now after deleting 4, find out the adjacent node of 4. There are 3 adjacent nodes, 3 to 6, but 6 is already deleted from the stack. So there are 2 nodes, 3 and 2. Which one we will choose? It depends on stack. After 4, the next node is 2, or now the topmost node is 2. So now from 4, how we can go backward? From 4 to 2. That is a backtracking. Okay, so now we can delete that node too. How? Before deleting that node, we have to find out whether there any unvisited node of 2. Look at the adjacent node of 2. Is there any nodes, are unvisited or left unvisited? No, right? Yes or no? This node 2 has how many adjacent nodes? 4 adjacent nodes. 1, 3, 5, and 4. That means it has one unvisited node. So can we take that node 5? Can we insert it in the stack and can we print it in the result? Is it possible?
No, madam.
Ma'am, no, ma'am. One.
Why not?
Possible, ma'am.
Ma'am, 5 is already, ma'am.
No, we didn't traverse that node yet. We haven't, inserted that node in the result yet. Among those 7 nodes, already 6 are visited. Only 1 node is left, and that one is 5. And now we are in this node. The current node is 2, and this node has 4 adjacent nodes. 3 are visited, and 1 is unvisited node. So can you take that node 5 in the stack, and can you print it here? No, it's not possible. In backtracking, we have to follow the order of the stack. In this stack, after 2, the next node is 3. So we have to choose this path or this direction for backtracking from 2 to 3. So now the current node is 3. Before deleting, before popping that node from the stack, find out how many nodes are unvisited. For 3, there are 4 adjacent nodes, 0, 1, 2, and 4. And all these nodes are visited. Then again backtracking from 3 to 1. So we'll use this direction from 3 to 1. Now the current node is 1, and 1 has how many adjacent nodes? 5, 0, 3, 2, 6, and 5. Among those 5 nodes, 1 node is now unvisited. The current node is 1, and for that node, we found unvisited. Hello?
Yes, ma'am.
Yes, ma'am.
Yeah, we found the unvisited node. So now can you take that node?
No, ma'am.
Why not?
Ma'am, because this is not the order of its statement.
This is not the order of the stack. Okay, fine. So now, if we suppose we didn't take that node 5, right? So that means the next one, so the next one will be 0. And 0 is 0 was our source node. And if we reach to that point, that means all the nodes are visited. Look at this. After 1, the next node is our source node. So before going to that node again, we have to traverse all the nodes. That's why here we can add 5. Is it the solution?
Yes, ma'am. Now understood, ma'am.
Okay, so there are 2 ways. One is at this point you can take that node 5. So what is another way? Again, look at the top of the stack. Suppose now we didn't delete any nodes. We didn't delete any node. So at first we want to delete 6 and then we'll go backward to which node? To the node 4. 6 to 4. And for 4 all the nodes are visited. Then we can pop that node from the stack. Okay, the next node is 2. So for 2 there is 1 unvisited node. Look at this. We are now in this point. There are two ways. At first we deleted 6 because 6 doesn't have any unvisited node. And we deleted 4 because 4 doesn't have any unvisited node. So now this is our stack. The topmost element is 2 and then 3, 1 and 0. So now here, when we use backtracking method, if we can't move forward, and here when we can move forward, if there is a connected edge between a node and its adjacent node, and if that adjacent node is not visited, then we can move forward. Otherwise, use backtracking method. So at this point, when we are at this point 2, so before using the backtracking method, again you have to find out whether any nodes are unvisited or not. Yes, one node is unvisited, 5. So if we add that node in the top of the stack, because in stack we can only use this end for inserting and deleting element. Suppose at this point we found an unvisited node that is 5 and we inserted that node in the top of the stack. So after that, here look at this, we can go forward. We can go forward, isn't it?
Yes, ma'am.
When we are at this point, 5 is the top of the stack. When we can traverse the node, if that node is the topmost element of the stack. So here from 2 to 5, 5 is the, when you traverse, when you use this, when you traverse the node 2, at that time we got an unvisited node 5. So now we have moved forward, that is 2 to 5, and 5 is stored in the stack, and this is the topmost node of the stack. So now we can traverse that node 5 and we can add it in the list. Is it clear? This way is also correct. And when you have a chance or you have the option to move forward, you can take that option. In this point, when you are in this point 2, the node is 2, we can see that one adjacent node of 2 is unvisited. So we can add that unvisited node in the top of the stack. So now if that element is at top of the stack, we can easily remove that node from the stack, or we can traverse that node. We can traverse that node. Okay, so now look at this. The current node is 5. Okay, so find out the adjacent node of 5. How many adjacent nodes are here? Only 2. That is 1 and 2. And all these nodes are visited. That means we can't go forward. We have to use backtracking method. So which path we'll use? We go to the stack. After 5, the next node is 2. So now we can use the backtracking method from 5 to 2. 5 to 2. The current node is 2. Now find out which nodes are the adjacent node of 2. 1, 4, 3, 5, and all nodes are visited. Okay. After that, again backtracking from 2 to 3. Okay. So here in this way, now 3 is the current node. Find out the adjacent node of 3. How many adjacent nodes are here for 3? 0, 1, 2, and 4, and all the nodes are visited. So we can delete that node. Now again backtracking from 3 to 1. So now we can use this direction from 3 to 1. So for 1, all the nodes or the adjacent nodes are visited. So again backtracking from 1 to 0. So when you reach this point 0, now find out the adjacent node of 0. 1 and 3, and these two nodes are visited. So you can delete the last node from the stack. And then after traversing all the nodes or after using the backtracking method, now this stack is empty. Is it clear? So which way we can use, the first one or the second one? So this one is the most effective. We can use the second path. If there is an option for moving forward, you have to take it. Okay, but if there is no connection between a node and its adjacent node, or if all the adjacent nodes are already visited, then use the backtracking method, that is DFS. Is it clear? What is the main difference between BFS or DFS, or how you can traverse the graph using that method DFS? Is it clear? So I'm explaining the second process again, DFS or depth first search. That means we're going to the depth of the graph. How? By visiting each of these nodes, and then we are taking only one adjacent node of that node. So we started from 0. After that, we have taken the adjacent node 1. There are two adjacent node of 3, sorry 0. These are 1 and 3. So you can just take any one of these two nodes. We took which one? 1. Right? So when we inserted that node in the stack, we can, that is the top of the stack, so we can traverse that node 1 and we can add it in the result. Now, after traversing that node, find out the next node, which is the adjacent node of 1. 1 has several adjacent nodes, just take 1, and we have taken 3. So now 3 is the top of the stack, we can traverse it and then we can add it in the result. So after traversing that node 3, now again find out its adjacent node, and we took 2. Okay, so now 2 is the top of the stack, traverse that node, then store its adjacent node, and we took which one? 4. After traversing that node 4, after inserting it in the result, now we can add its adjacent node, which is 6. Now 6 is the top of the stack, and we can traverse it or we can add it in the result. Now the problem arises here. This is a dead end because 6 is connected with 1 and 4, and 1 and 4 are already visited. That's why we can't go, we can't move forward. This is a dead end. Okay, so how we can, but we didn't traverse all the nodes. Look at this, there are only 6 nodes, but we can't traverse 5 now because there are no direct connection between 6 and 5. Okay, so now backtracking. How we can go backward? Just look at the stack. We are now in this point, in this node, this is our current node. And if we want to go backward, then choose the next node of the stack, that is 4. So we can go using this path from 6 to 4. And when the current node is 4, then find out all the adjacent node of 4 just to check whether any unvisited node is here. But for 4, all the nodes are visited. Then again backtracking, look at the stack, the next node will be 2. So you can use this path from 4 to 2. And here in this point, all the nodes are not visited, all the adjacent node of 2 are not visited, so we can move forward. So now this is the top of the stack, 2 is the top of the stack, that's why we have added, we have inserted the next node as the top of the stack, that is above 2. So now this is our new stack, where 5 is the topmost element and it's not traversed yet. So we can traverse that node and we can add it in the result. Okay, so now which nodes are the adjacent node of 5? 1 and 2, and these are visited nodes. So now we can use the backtracking method again. Just look at the stack, the next node will be 2. So now the direction is from 5 to 2. Then again backtracking because for 2 all the nodes are visited. And from 2 to 3. And in this point, all the nodes of 3 are visited. Then again backtracking from 3 to 1. And at this point, the adjacent node of 1s are visited. Then again backtracking 1 to 0. 0 was our source node, and all the adjacent node of 0 is already visited. So delete that node from the stack. And now, after traversing all the nodes or after performing this backtracking method, we got an empty stack. And this method is called DFS. Is it clear? Hello. Is it
Yes,
clear?
ma'am. Yes, ma'am.
Okay, so I think this is it for today. So we just discussed only one topic, that is graph traversal. Okay, so there are two approaches for traversing all the nodes in graph. One is BFS, another is DFS. So you can do one thing, just construct a connected graph, and then you can traverse all the nodes of that graph. Okay. So now please respond. 1.
Yes, ma'am.
1, 2. Sorry.